I'm pleased to be able to talk a little bit about our control channel design for multi-user MIMO. Actually, where is the clicker? Oh, there we go. So first off, what is the control channel? I'd assume most people here know what it is, but really in a wireless communication system, it's anything that isn't data. And there's actually quite a few operations that you have to do to set up and maintain a high throughput wireless link. So the reason we actually got interested in this is I've been building real-world mini antenna base stations for the last few years, and while we were building our reference design, our real-time reference design, we realized that traditional control channels aren't very practical for multi-user MIMO. At the heart of this problem is the multi-user MIMO gain gap. So the way that multi-user MIMO works is that it actually is multi-user beamforming typically. And what that means is it's actually taking all of the transmission power from all of the antennas in the base station and sending it over very narrow beams to the intended users. So effectively what you're actually doing is extending the range of the base station by doing the beamforming. What's even worse is that when you're actually building this system, you don't have a total transmit power constraint. You actually get more power for every antenna you add if you have symmetric antennas, which is usually what you have in these mini antenna base stations. So what that means is that you can actually get this gain gap that grows with m squared as you add antennas, because you not only add more power to the base station, but you actually add more directivity when you're doing that beamforming. And then you split the power among the users, so you actually have a factor of k that you're splitting there. But most multi-user MIMO base stations do actually serve a single user when there aren't more users to serve. And then next, you actually get a similar gap on the uplink. But the thing is you aren't increasing the transmit power on the uplink, so it only scales with M. Now at this point you might be wondering, well, why don't we send from all of the antennas on the base station simultaneously to get an in-full transmission power gain? Well, the problem there is that the existing multi-user MIMO techniques for control channels don't work for synchronization or channel state information collection, CSI collection. So for CSI collection, that's actually a fundamental bottleneck, because CSI by definition is the information between two antennas. So multiple antennas don't really help you there. For synchronization, the problem is that the existing techniques deployed actually cause time distortion. So for example, in 8.11, they intentionally do something called cyclic delay diversity, which means that they're delaying the symbols sent from each antenna. And this is so that they spread out that power omnidirectionally, but the result is that you actually get time distortion. And that actually causes the performance to degrade substantially as you start increasing the number of antennas. So essentially it doesn't scale at all. So what we're left with is this classic chicken and egg problem. I need to synchronize with the users to be able to send them data and get their CSI and everything else, but until I have that, I can't communicate with them. So that's actually what motivated us to do this from scratch control design for multi-user MIMO, which we call Faros. So Faros actually means lighthouse in Greek, or beacon even. And so it's actually analogous to the way we ended up solving the problem, which is sweeping these very strong beams, similar to the way a lighthouse sweeps its light. So on Monday, we realized we actually missed a golden opportunity to call it Eiffel, since the Eiffel Tower actually does something very similar at night, where it's sweeping those open loop beams. So anyway, our design is guided by two key insights. Our first key insight is that we should send as much as possible over the control channel, or over the, multi-user MIMO mode, the much more efficient multi-user MIMO mode. So that leaves us with only these critical control channel operations that are required to establish that efficient multi-user MIMO mode, and those are synchronization, association, CSI collection, paging, and random access. And so that's really what I'm going to be dealing with in this paper, and you can use existing techniques to address the rest of the control channel issues, such as scheduling. Our second key insight is that synchronization and association are not time critical, which allows us to make very important performance trade-offs and basically reduce the overhead of our control channel to something that's pretty much negligible, as you'll see. So our first problem is, how do we solve that gain gap? Well, probably the primary source of that solution is open loop beamforming. And open loop beamforming is really perfect for this because you don't get any time distortion, so you can actually establish that synchronization very easily with it. And the power scales with m squared as well, because you're still using all m antennas to transmit, and you're still getting that directivity from all m antennas. The problem is that quite obviously you're not going to send that over the entire coverage area, so you have to sweep those open loop beams, which requires even more time. And finally, there's still actually a little bit of a coverage gap there because you're never going to be able to point those open loop beams directly at your users. So the next point is fairly obvious, is that you need to use a coding gain as well to complete that coverage. So the coding gains are really nice because they're very flexible. You can basically do them per deployment. It's very easy to adjust that coding gain for what you need, and then you can get full coverage there. So what we're left with is actually a very flexible system where you can reduce the number of beams and increase the coding gain and still get the same desired coverage, or you can even increase both the coding gain and the number of beams and increase your range accordingly. So now let's take a look at how we actually apply this to our control channel design. If you look at any multi-user MIMO frame structure, you have four basic stages. The first one is identifying the base station and getting synchronization with that base station somehow, usually through like a preamble and LTS, which will also notify you of the packet. Next, you need to collect channel state information to all the users you're going to transmit and receive from. And finally, you actually have your actual data transmissions in the downlink and uplink. And then this repeats indefinitely for whenever you're needing to send data. In Faros, what we do is we actually encode the base station ID in the beacon as an encoded signal, and then we sweep that. So to establish synchronization and identify the base station, all you need to do is to wait for that synchronization sweep to hit you. And it may not hit you directly, but the coding gain takes care of that. So as long as you can detect that, you can identify the base station and achieve time frequency synchronization. So next, when you want to associate, we have dedicated slots for random access. So you simply send an uplink pilot in this random access slot, which is fairly similar to the way LTE does it. And that will actually allow the base station to collect CSI for that user. And now you're in multi-user MIMO mode, and you can send and receive the rest of the control channel over that multi-user MIMO mode, including scheduling a dedicated pilot slot just for that user for subsequent frames. Similarly, when the user goes to sleep and wakes up again and says, I need to send data, now all it has to do is send an uplink random access request in one of those dedicated slots, and again, you get the multi-user MIMO mode after that. So for collecting CSI, there's nothing too special here. The only thing that we note is that you really need to be doing OFDMA, because what OFDMA allows you to do is have all your users sending simultaneously for the corresponding amount of time, which basically means you get a k-fold gain, where k is the number of your users. But even that's not going to fully cover that m-fold gain gap, so you need to code it even more. Now, if you look at that compared to existing systems, you can think of existing systems as having the baseline for coverage area. So you could actually send the same length of pilots that you're currently doing and getting the same range. What we're saying is actually you don't even need that much transmission power on your mobiles. You can back it off and replace it with a coding gain, which you only need to leverage during this pilot slot. Finally, the base station may also have incoming data for the user. Say you get called, or you even want to run a server on your phone, or whatever you're doing. What you do is you can actually send a paging signal simultaneously with the beacon, but use the last known user location to send those paging signals, which are also encoded using the same code book, so they're orthogonal to the beacon ID. So if you look at the overhead, the fixed overhead for this system, it's actually very negligible for a number of practical systems, even if you scale up to even thousands of antennas. Yeah. So the trade-off here is actually that you're, by increasing the number of beams you send or the frame length, you're actually increasing the latency to synchronization. But really all that affects is the association delay, which, since it's a one-time cost, is not really that big of a deal. But it's something you can trade off by reducing your frame size or decreasing the number of beams that you're sweeping. So next, we actually implemented Faros on Argos. We actually presented this Argos V2 as a demo 2 years ago at MobiCom. We tested it in an anechoic chamber, and this is with an 80 antenna setup right here, as well as indoor with both 104 and 108 antenna configuration. For the clients, we use the Argos mobiles, which are fully autonomous mobile clients. They're actually battery powered, and we get feedback through a wireless link, which makes it very, very convenient to deploy these situations and test everything. For the open loop beamforming, we chose Hadamard, which is a very good selection because it has perfect peak to average power ratio for the open loop beamforming weights. It also provides full spatial coverage without having to calibrate for hardware effects or the environment. For the encoding the base station ID and user IDs, we use Kasami sequences, and those are well known in the community for being good for establishing time synchronization because they have a low bounded streaming correlation both with themselves and other sequences in that data set. Code book. Here are some example locations of where we performed the experiments. We did experiments in 5 base station locations. We did 68 indoor user locations and 32 anechoic user locations. At each sweep, during each beam, after each beam, we'd stop and measure whether we had any false positives at any of the mobiles or the true positives. And that actually resulted in over 1 million measurements across this measurement campaign. So our primary result is just showing that these beacons can be detected and that they increase the range of the base station very substantially. So with the 128 length code on Faros, we actually see an over 40 dB increase in range compared to the traditional single antenna. Next, one of the critical issues that we see with Faros that we don't have in traditional control channels is that the problem is when we try to page users, they may have to wait for that sweep. So as I mentioned earlier, what we want to do is we want to use the user's last known location. So they always have a last known location because they had to associate and we got CSI then. But now what we wanted to do is say, well, we use the last known user location. Let's see how quickly or how much that will reduce that paging delay. So we saw overall it would reduce it 4-fold. But that's actually kind of selling it short because when a user is close to the base station, it will almost always receive that paging signal, even if it wasn't pointed at it. So when you look at the low RSSI, so when the users are further away on the cell edge, we see actually a worst case performance increase of over 20-fold. Oh, that was back. Sorry. So another thing I wanted to mention was that actually because we were pausing after every beam, it allowed the environment to change. It's actually multiple seconds for us to collect all the information and send the next sweep. So this is actually probably underselling how well the paging performance would work in the real world. But we also did some real-time experiments outdoors so that we could actually walk further away with the mobiles. And we actually got up to 250 meters away from the base station before we had to go behind a building and lose that beacon synchronization that we were getting. What's interesting there is we actually were only using 10 milliwatts of total power, so we basically turned the power as far down as we could on all of our base station antennas, so it was under 100 microwatts per antenna, so that was actually pretty cool to see. I also want to mention that we're using this as our real-time framework in Argo, so we're doing high-resolution channel measurements using this to maintain synchronization with the mobiles and collect orthogonal CSI from all of the mobiles. And finally, on a more fundamental level, Faros actually allows the base station designer to trade off these space-time code resources to finely tune overhead versus the desired coverage area of the base station. So in closing, I'd like to reiterate that Faros is a highly efficient, from-scratch control channel design for many antenna multi-user MIMO. We implemented it on Argos and saw that it was able to give us over 40 dB of gain with 108 antennas set up. And finally, it actually is solving a very critical barrier to the adoption and implementation of mini antenna multi-user MIMO. And basically what it allows you to do is decrease the per antenna transmit power very, very substantially, which saves a lot of space, power dissipation, and a lot of other big problems. And finally, I'd like to thank my co-authors, Bir Javed and Lin Zhang, as well as my other collaborators, and especially NASA, who let us use their anechoic chamber, which was pretty awesome. It was a very, very cool anechoic chamber. And with that, I'll take questions.